In this lecture, we are going to study how to represent the transfer functions that describe the behavior of a given system as block diagrams. In a block diagram, transfer functions of the system elements are represented by individual blocks. Inputs and outputs that flow to and from the system elements are represented by lines and arrows, and their terminations define the manner in which different parts of the system interact. This is very useful when you have complex systems. It's an easy way to now identify how transfer functions interact with one another and what the inputs and outputs of the different parts that constitute that systems are. By the end of this lecture, you should be able to represent a control system using block diagrams, simplify block diagrams, and find the open loop transfer function of a closed loop system. You should be able to go from transfer functions to block diagrams and vice versa. The idea behind block diagrams is very simple. We want to represent transfer functions as blocks with an input and output. And for complex systems, we can now put many blocks together that will represent how these transfer functions are connected. Here is one example of a simple control system. We have a process that is to be controlled. We have the actuator that provides power to the process and the controller. The output of the process is measured using a sensor, which has a transfer function in itself. And this block diagram represents how the controller, actuator, process, and sensor are put together to form a feedback control system. When each of these blocks has a transfer function, one question that we want to answer in this lecture is how to find the closed loop transfer function, that is y over x. We can also go the other way around and start from equations and then represent those equations as block diagrams. Here we have a spacecraft platform that is governed by a set of 4 equations. We have inputs and outputs and some internal variables. When you look at these transfer functions, it is hard to see how they are connected. But if you're able to represent them in a block diagram, the relation between input and output would be much more explicit. How can you represent this system using a block diagram? A block diagram represents the relation of a system variables graphically. Here we have the relation between the input voltage and the output position of a DC motor. For a DC motor, the input is Vin, that is the voltage applied to the motor, and the output could be the position. The block diagram, in this case, will then have a transfer function between the output and the input. When Vin is given to that block diagram, that results in an output theta of S. We can also have block diagrams with multiple inputs and outputs. But in the context of this course, we're going to stay with single input, single output block diagrams. To create block diagrams, let's start by looking at the basic building elements that will constitute complex block diagrams. Each of these building elements will create a specific operation, will represent a specific mathematical operation. The simplest one is the transfer function. Consider the transfer function g of s. The input to a system is x. When we pass x through that transfer function, we get y, the output. This representation is equivalent to y equal to g of s times x, which is the very definition of the transfer function. Output divided by the input is the transfer function. When x is applied to the system, x times the transfer function gives the output y of s. And this operation is represented by this block diagram. The second basic building element is the gain function. While transfer functions are represented by a square or rectangle, gains are often represented using a triangle. This is to indicate that what is inside that gain is not a function of s, it's simply a constant. Consider the variable x that passes through a gain alpha, and let's assume that the output is y. The gain building element is equivalent to writing y equals to x times alpha. The last building element is the sum, that is simply represented by a circle. In the absence of any additional information, assume that this represents a sum, and when a negative sign is added to one of the inputs to that sum, then that represents a subtraction. If you call the output here z, we can write that z equals to x plus y. And in the second case, because of the addition of this negative sign, z equals to x minus y. And this is all we need. These are the basic building elements that we can now put together. So in the first one, to recap, y equals to g of s times x, where g of s is a transfer function. In the second one, y equals to x times alpha, where alpha is a constant, hence the triangle to represent a constant. And the last one, z equals to x plus y, or x minus y if a negative sign is present here, or even y minus x if the negative sign is there. We can now put these basic building elements together and represent complex systems. Let's get right into it with a DC motor. The objective in this example is to find the block diagram that represents the structure of a DC motor. A DC motor has two main parts, an electrical part and a mechanical part. Let's start by modeling the mechanical part and creating the transfer function for it. The electrical part can be modeled using a RL circuit. The voltage input is V, that develops a current I, and then the motor starts to rotate. When the motor rotates, it induces a back electromagnetic voltage to the RL circuit, and you're going to call that a voltage Vm. Vm is a function of the motor speed. Using Kirchhoff's law, we can now find a relation between V and I. Let's write that relation in the frequency domain directly. V of S equals to the voltage drop across the inductor plus the voltage drop across the capacitor, which is I times R plus Ls respectively, and plus the voltage induced because of the motor rotation Vm. We can now find an expression for I of S, the current, that is V of S minus Vm of S divided by Ls plus R. This is the first relation that represents the electrical part of the motor. As the motor rotates, a voltage is induced in the motor's armature. This voltage is called the electromotive force or voltage. That is what we call Vm. For DC motors, it follows that the voltage induced by the motor rotation is simply proportional to the speed of the motor, where omega s is the speed and Km is the back EMF constant, which is a constant that depends on the construction of the DC motor. This is now our second equation. Now we have completed the electrical part of the circuit, and we see here that the electric behavior is influenced by the mechanical properties of this system as well. So now let's go to the mechanical part and model that. Now let's look at the mechanical part. As a current flows in the RL circuit, that current results in a torque being applied to the motor, and let's call that torque T of S. The rotor has an inertia J and the speed omega t. Let's further assume that this motor drives a load. This is a torque that comes from an external load that is applied to the motor, or the external load that the motor drives. We can now do the sum of all torques acting on the motor, which is equal to the moment of inertia times the acceleration, which is equivalent to the derivative of speed. The torques applied to the motor include the torque developed because of the current I, which is the motor torque itself, minus, assuming that there is friction between the shaft and the armature, and the viscous friction coefficient is B, we have a torque now that opposes the speed, so minus B times the speed, and we have the load torque, Td, an external torque applied to the motor, and this is equal to J omega of S times S. Remember that this S represents the derivative of omega, which is the angular acceleration. From this we have T of S minus Td of S equals to omega of S times Js plus B. We can now create an expression for the speed, T of S minus Td of S over Js plus B. This is another expression that we need to model the DC motor. Now let's go back to this developed torque. In a DC motor, it turns out that torque is simply proportional to the current. This is the armature current in the motor, and Ki is what we call the torque constant, which is a constant that depends on the construction of a given DC motor. And this is another expression that we have. Now from this analysis, we created four expressions. And now let's see if you can write that in the form of a block diagram. Here is a summary of four equations we determined before. Now let's try to write them in the form of a block diagram. The input to this system is Vt, is the voltage applied to the motor. And the output, in this case, is the speed. It's always a good idea to start from the input. The input Vt or Vs shows up in the first equation. Now let's try to recreate the first equation. The input is V of S. If we now subtract from V of S, Vm of S, this results in Vs minus Vm of s. If you now divide this by 1 over Ls plus R, the output here is simply I of s. Moving on, I of s shows in the third equation. If you now take I of s and multiply that by the torque constant Ki, the output is T of s, the torque that the motor develops. T of s shows in the second equation. If you now subtract Td of s from T of s, we get the top of that expression. And when you multiply T minus Td by 1 over Js plus B, the output is simply the speed. The speed shows in the last equation. When the speed is multiplied by Km, that is the speed constant, the output here is simply Vm, the back EMF force, the induced voltage to the stator. And this is exactly what we needed in the input, and this closes the feedback loop. Open that using Simulink and MATLAB and evaluate the step response of the motor.
The document posted on Canvas has two files. The first one is a MATLAB file and the second one is a Simulink file. Let's start by opening the MATLAB file. This MATLAB file declares all variables that we are going to use in the Simulink model. Here we have the input voltage to the DC motor, the winding resistance, the inductance, the torque and speed constant, the inertia and friction. Run the code to send these variables to the workspace. The workspace is shared with Simulink. Now these variables can be used in Simulink. And then open the Simulink model. This Simulink model is the exact representation of the block diagram we covered in the lecture. We have two transfer functions, the electric and the mechanical transfer function, two gains, an input, an integrator, and the scopes that will plot a given variable over time. Let's open the input. In the input block, we see that we have a step input. The input voltage starts at 0 and goes to Vin at 0.05 seconds. Let's run the code and look at the input voltage. You see here the input going from 0 to 12 volts at time equals to 0.05 seconds. And now let's look at the speed. We can see that when the voltage is applied, the motor starts to rotate and settles at a given value. The position is the integral of the speed, and we can see here a small transient, and the position then keeps going up in a steady state. Let's look at the current. The current starts at 0, and when the voltage is applied, there is a spike in the current around this point, and then the current decreases and settles at around 5 amps. This peak can be explained by the fact that when the voltage is first applied to the motor is not rotating. Thus, this feedback loop here is 0. The voltage applied to the motor is 12 minus 0 equals to 12 volts. When the motor starts to rotate, the speed is non-zero. So the back EMF force that comes from this feedback is also non-zero. So you now have 12 volts minus a non-zero value. So the voltage applied to the circuit is less than 12 volts. The voltage decreases, so does the current. If you now wish to change the parameters in this model, we can go back to the MATLAB file and change one of them. Let's change the viscous friction coefficient. Run the code again and run the Simulink code one more time. Let's look at the speed. We can see now that as we decrease the viscous friction coefficient by a factor of 2, the maximum speed is increased. We can now evaluate the influence of any of these parameters in the time response of the motor by simply changing these values in MATLAB.
Now that we went from equations to block diagram, let's try to go from block diagrams back to equations. There are basic operations that we can perform to help us during that process. The first one is combining blocks in cascade. Here we have two transfer functions that are being multiplied together in a line. We can simplify them in one single block diagram by simply writing g of s times h of s. And in both cases, y of s is simply g of s, h of s times x. The second basic operation is to move a pickoff point ahead of a block. In this example, y equals to h of s times x. And let's assume that this pickoff point needs to be moved ahead of the block for simplification purposes. If you now move this pickoff point ahead of the block, the output signal here is x. So to maintain the same signal, we must now multiply that line by h of s so that the output becomes h of s times x, which is exactly what he had in the beginning. So the output here originally was h of s times x, and the output in the new block is again h of s times x. So the signal is maintained. The next basic operation is moving a summing point ahead of a block. The summing point is behind the block in this example, and we wish to move that past the block. We can write an expression for y if in this case here, in this point in the diagram we have x plus z, and we can then write that y equals to x plus z times h of s. If you now wish to move the summing point ahead of the block, as shown in the second case, we need to manipulate the block diagram so that the expression for y doesn't change. In this case here, the signal z would have to be multiplied by h of s to maintain the same signal. Notice that in the first input to the sum we have x times h of s. The second one we have z times h of s, and y can be written as x h of s plus z h of s. Factoring out h of s gives exactly what he had before this manipulation. Now let's do the opposite operation. Let's move a summing point behind the block. What is the output here? The output there is x times h of s, which is y, plus z. So if we call this signal here q equals to x h of s plus z. Or y plus z, and y is h times x. If you now take this sum and move it behind the block, what do we have? If you don't do anything, the output of this block diagram would be here, and it would read as x plus z times h of s, which is x h of s plus z h of s. This is not what we got here, because in the first case, z is not multiplied by h of s. But to compensate for this manipulation, now z needs to be multiplied by 1 over h of s. And now the new output y is simply x plus z over h of s all times h of s. And this now simplifies to x h of s plus z. And this is indeed what he had originally. One of the most important operations is to eliminate a feedback loop. This must be very clear at the end of this lecture, because we are going to use this throughout the course, and this will only be explained here. Let's consider this feedback loop. The input is x, and the output is y. Y is now fed back to this sum that compares the input and the output. And at this point here, the signal is x minus y. And past the block diagram, now the signal is x minus y times h of s. The signal at this point is y. So the expression for y of s is simply x of s minus y of s times h of s. We can now multiply this out and move y of s to the left. Factor out y of s. And now isolate for y of s. This now gives the explicit relation between x and y as h of s divided by 1 plus h of s, which means that when the feedback loop is eliminated, we can simply write h of s, the line function, divided by 1 plus itself. And in this block diagram, we have the exact same relation. In case we have a positive feedback loop with a positive sign here, the only difference will be y equals to h of s divided by 1 minus h of s. So for a negative sign, 1 plus h of s, and for a positive sign, positive feedback, 1 minus h of s. This is a very important operation because it allows us to eliminate any feedback loop and further combine transfer function to simplify the block diagram. Now in the previous example, the feedback function had a unit feedback, but in this case we also have a transfer function in the feedback line. Let's see if we can simplify this one. The signal in the output is y, so the signal past g of s is y times g of s. which means that the signal past the sum is x minus y times g of s. And the signal past the h of s is x minus y g of s times h of s, which is y. So the expression for y is simply x minus y g of s times h of s. Now expanding the equation and solving for y gives this simplified version. To eliminate now a feedback loop with a feedback function g of s, this simply becomes h of s over 1 plus the multiplication of these two functions. We'll refer to h of s as the line function and g of s as the feedback function. So line function divided by 1 plus line function times feedback function. And again, in case of a positive feedback loop, this would become h of s divided by 1 minus g of s times h of s. Let's do a simple example. This example that we started with in the introduction. The input to this feedback loop is x and the output is y. We have three functions. One represents the controller, one the actuator, and one the process. And you have a feedback function h of s, which represents the sensor. What is the closed loop transfer function y over x? We know that these three blocks here can be combined into one, which means that the block diagram can be rewritten as follows, where these three functions become one because they are in cascade. What is the next step? Now the next step is to eliminate the feedback loop. This feedback loop has a line function h of s. So let's call this function a and this function b. We know that to eliminate that specific feedback loop, that will result in a over 1 plus, because of the negative sign here, a times b. So this gives x as the input times a, the line function, c of s, a of s, g of s, divided by 1 plus c of s, a of s, g of s, times h of s. And the output is y. So the transfer function is y of s over x of s equals to cag over 1 plus cagh. Now let's go back to the DC motor. We went to the equations to the block diagram model. Let's now go the other way around. Start from the block diagram and go all the way back to the equation. What is the transfer function theta over V, that is the position as a function of the voltage, when T of D equals to 0? There is no load. When T of D equals to 0, then we are injecting 0 here, and this sum disappears. This means that these three blocks can be combined into one by simply multiplying them. And the block diagram simplifies to this. The speed is here. What is the next step? We cannot multiply 1 of s with anything because here we have a feedback loop. So first, let's eliminate that feedback loop. This feedback loop has both a line and a feedback function. Let's call the line function a, the feedback function b. If you simplify that into a single block diagram, that will be a over 1 plus ab plus, because this feedback loop is negative. So this will simplify to ki over ls plus r times js plus b divided by 1 plus ki ls plus r times js plus b times km. Now here we can find a common denominator. The common denominator is ls plus r js plus b. That times 1 gives itself, plus ki km. Now this denominator cancels with the top, and this will simplify to ki over ls plus r times js plus b plus ki km. So now the entire feedback loop simplifies to ki over ls plus r js plus b plus ki km. And this once again represents this part of the block diagram. The output is omega s here that passes through 1 over s and gives theta s. Now these two blocks can be combined, and the output now becomes theta s. So theta s over vs equals to ki s ls plus r js plus b plus ki km. And this is now the transfer function between the input and the output of the DC motor. So here's the transfer function we just calculated. Notice that if you look at the transfer function, we only have access to the input and output of the system. But if you consider the block diagram instead, we have access to intermediate variables, such as the current, the speed, and the back EMF. If the DC motor is well built, the armature time constant is negligible, because the inductance is very small. In that case, we can neglect the inductance and convert this third-order polynomial into a second-order transfer function as follows, where tau is a constant given here. Now let's do a few exercises on block diagram simplification, going from transfer functions to block diagrams and vice versa. These examples will be posted in separate videos. Thank you.